Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.
Well, it's very nice to be back in front of a Saturday Morning Physics audience. As some of you longtime Saturday Morning Physics fans know, I have helped to organize this series for many years and had the pleasure of being in here on a lot of Saturdays. For the last year or two, some of these new responsibilities, like being the undergraduate chair, have made it physically impossible for me to also do that. But that doesn't mean I can't come back and occasionally give a lecture. And it's a real pleasure to come back to the Saturday Morning Physics environment again and do that. This lecture that I want to give today is an important one to me because this realization that the Big Bang cosmology, which we have gradually been working toward for the last 80 years or so, this realization that it has arrived as a scientific theory, as something that is robustly proven, is very new. It's really only come to that state in the last 10 years. I was part of that, a small part. But being around when it happened was one of the most exciting things that has ever happened to me. And so it's really important to me to get the message out about this and to help people to understand what has changed and how it is we've come to believe that our universe has this extraordinary origin. So we're going to talk today about a question, so basic that people at all times and in every place throughout history have been compelled to ask it. What we're going to talk about is the origin of things. Where does everything come from, and how did it come to be? This question of origins, of trying to understand the history of things, is intimately intertwined with being conscious. Having consciousness is thinking about history and the future, and not just existing in this instant. So it's a really fundamental thing. So people have always had stories to explain the origins of the world and their universe, and these are called cosmogonies. They're also usually, the story itself is usually a central part of the cosmology of a people. And a cosmology is something a little bit more than just a story of the origin. It's a whole framework, and the Oxford English Dictionary calls it the science or theory of the universe as an ordered whole, and the general laws which govern it. This kind of story or science or theory of the universe is what I want to talk about today, this kind of cosmology. Essentially, this is a story of how things came to be and why they are the way they are. Now, any system of understanding which couldn't give you this story of origins, which could only talk about the here and now, would be pretty unsatisfactory. And if science could only do everything that it does now, make your microwave work, let your cell phone work, and stuff like that, but had nothing to say about the origins of things, it would be a sorry thing. It would be unsatisfactory. We need to understand these things, and the fact that science can present us with answers for some of these questions is an essential part of science. So during this lecture and the next one, which will happen 2 weeks from now on April 2nd, I want to talk about a particularly remarkable story of origins, this Big Bang cosmology. It's only now in the early 21st century that we can say with real confidence that this Big Bang really happened, as much as we can say anything about history. As much as we can say that the Earth is 4.5 billion years old, as much as we can say that once there was a massive glacier pressing down on the state of Michigan. All of these kinds of things are based on evidence, and the evidence for the Big Bang has risen to the level now where we have to take it as seriously as we take all these other pieces of history. All right? Before we continue, though, I want to make a few disclaimers. This is a very broad subject, one of interest to many people in many ways. And when I talk to you about it, I'm a scientist, and that's mostly all I am. I'm not a historian, I'm not a sociologist, I'm not a philosopher. And I may say things in those areas, but I don't do so particularly as an expert. When I tell you about the science, I can speak with authority. When I tell you about some of these other things, I speak very much as one of you, as an educated member of the community who's thought about these things and read about them, but I'm not the world expert in those things. So you have to understand that, that distinction. When I talk to you about scientific things, I can stand on very firm ground. When I talk to you about other things, it's just as one of you, all right? Okay, let's get started. So we're going to talk about origin stories, but I'm not going to talk about this origin story. I want to talk about other kinds of origin stories. A lot of origin stories that people have had throughout the years go something like this. They say, in the beginning, there was formless chaos. And out of that formless chaos, there emerged some kind of initial forms. Things not like us, but something before, initial forms. Maybe they were gods, and these gods struggled and fought with one another, and gradually made the things that make up our world, and brought forth mortal life, and created the world that's around us. Now let me tell you a modern creation story. In the beginning, there was formless chaos. And into this chaos, some basic elements were created. Initial form was somehow imprinted in that initial chaos. And from that initial form, ever richer structure has grown, and more complex elements have emerged. Eventually, this brought forth mortal life and the world which is around us. It's kind of a remarkably similar story, except that it doesn't have a very personalized cast of characters. It's interesting to me that the story is so similar to what we think today. So let me tell you about this story in somewhat more modern terms. This is the modern picture of the origin of the universe, and I know you heard some about it from Fred Adams last week if you were here. 13.7 billion years ago, give or take 0.2 billion years, the universe was very hot and very dense and made of quarks and leptons and radiation. It was almost completely uniform, and it was expanding. That's what it looked like then. Since that time, it has continued to expand, with its overall temperature dropping along the way, and a few things have happened. About 3 minutes into the Big Bang, the temperature became low enough for quarks to bind together and to form protons and neutrons. And in a flurry of bonding, all the matter that's in the universe came together to form these nucleons, protons and neutrons, and to make the universe be constructed out of 76% hydrogen and 24% helium. When the universe was about 380,000 years old, plus or minus about 10,000 years, it cooled off enough for neutral atoms to form, and rather suddenly the universe became transparent and light began to propagate freely through it, and it has continued to do so ever since that time. Ever since that time when the universe became transparent, it has continued to expand, and we now know that it has expanded since that time by a factor of 1,088 plus or minus 2. So we really know how much the size of the universe has changed since that time. At this time when atoms were formed, the universe was also incredibly uniform. Same density everywhere. There were fluctuations about 1 part in 100,000. And you can picture that in your mind by imagining Michigan Stadium and adding 1 person or removing 1 person. That's the kind of change in density that existed then. Since then, those initial fluctuations have been amplified by gravity and grown to form the galaxies and stars that we see around us today. In those stars, gravity compressed the atomic nuclei in the center, causing them to burn and to accrete together hydrogen and helium to make the heavier elements that exist in the universe. All of those heavier elements, every atom of carbon, nitrogen, and oxygen that's in your body, was once at the core of a star. That's how they were made. That's where they came from. Some of those stars, when they ran out of fuel, exploded and very nicely sent out this fuel, these enriched elements, out into the universe so that they could then cool and form planets. About 4.2 billion years ago, that's what happened here on the Earth. The Earth condensed out of this enriched material from previous stars and formed a planet. About 3 billion years ago, roughly, life emerged on the Earth and began to evolve and created the incredible array of species that you see outside right now. Over the history of life, 99% of those species have become extinct. It's a continual process of change. About 100,000 years ago, people showed up, started to think about these questions and try and answer them. So that's the modern story. In very brief précis, the story of this Big Bang cosmology that you see in this nice picture here. It's kind of a crazy story, and it's difficult to believe. And so when you go and you ask yourself why you should believe it, I think you have to think a lot about the 2 kinds of influences that should help you to understand and to believe it. There are 2 kinds of arguments that we might use. There's arguments from authority. When a scientist comes and tells you that's how something is, you can judge the reputation of that scientist and decide whether or not you believe you should believe them. Right? This argument from authority is very important, but it is not enough. The other thing that we have in science is evidence. and including evidence which comes from far beyond our senses, things that we can only see with microscopes, things that we can only see with telescopes. It's not just what is obvious to your eye that we can learn about the world. Now, these two things, authority and evidence, mix extremely richly in science, and if it weren't that way, science could not work. We have to have this mix of authority and evidence. Without authority, every one of us would come to the universe absolutely fresh and uninformed, and we would have to discover everything. That would never work. And in fact, before we had a system by which authorities could learn what everyone else had learned and share it with other people, science progressed very slowly. It's that system of relying on what other people say that enables us to create science the way we have today. So authority is important, but it's also essential that there should be absolutely rigorous review of authority, and that review comes from evidence. If an authority tells you something and cannot present the evidence to prove that it is so, then of course you shouldn't believe it. You may not have to demand every little detail from that authority. After all, that's why they're an authority. They've earned the reputation of being honest and telling you what is true. All right? The sharing of this evidence through publication is what enables the establishment of authority and for people to learn and to build up things. This particular story that we're going to talk about today, the story of the Big Bang, is a great one because it involves a wonderful mix of these things. At different times there were authorities saying, I'm pretty sure this is how it must be, and at other times evidence would come along to really shake things up. And so we'll watch this whole story mix as it goes along here, and you'll get to see the relative influence of these different things. All right, what we're going to do today is first I'm going to give you a little bit of background for cosmology by talking about 4 little subjects which relate to the Big Bang cosmology. We're going to talk about the Copernican Principle, about the idea of gravitational instability, the fact that the finite speed of light gives us a kind of cosmic archaeology, and then we'll mention a 4th thing, which is a nice little paradox, which was an early clue about cosmology. The rest of the lecture we'll spend talking about early evidence for the Big Bang. We'll talk about the original evidence for the Big Bang, the fact that the universe is expanding. Then we'll talk about the implications of that expansion, the fact that an expanding universe now implies an early universe which was dense and hot. And then we'll see the evidence for that early universe in the form of thermal radiation. We can actually see the heat from that, and also the dominance of light elements in the universe, the fact that the universe is mostly made of hydrogen and helium. All right. The first thing I want to talk about is this Copernican principle. It's an idea which has been gradually growing in cosmology for the last 500 years. It's perfectly natural that we should all come to the world thinking that we are, in fact, the center of the world and that everything focuses on us and we're the most important thing that there is. Copernicus was one of the first people to bring back to light, let's say, the idea that the Earth was not, in fact, the center of the universe, but might orbit around the sun. Since that time, of course, we've learned that the sun is nothing special either and just orbits around like every other star in the galaxy, and that our galaxy is nothing special, but just another one of the galaxies which goes around. In the last century or so, this idea has been expanded into a grander notion, which is now called the Cosmological Principle instead of the Copernican Principle, and it states that no place in the universe is special. The universe is homogeneous. It's essentially the same everywhere. No direction in the universe is special. It's isotropic. It looks the same no matter which way we look through the universe. And there's even a stronger form of the cosmological principle that says no time in the universe is special. And that's a particularly interesting one because it seems to be wrong. The universe does have a history. It's not the same now as it always was. All right? So that's something which we'll set aside a little bit until the next lecture. An important fact about cosmology is the notion of gravitational instability. And here's just a picture to remind you of gravitational instability, an overhanging rock. We usually think of gravity as the thing that causes us to fall to the floor, but gravity is a much more general thing. Gravity is a force which exists between any 2 objects in the universe that have mass. Any objects which have mass exert a force on one another and consequently are pulled together. And it's always together. And that's essential because it drives evolution in the universe. If you wanted to set up a stable, infinite, permanent universe, you would put stars out there in the universe and they would pull on one another, and it would collapse. You can't have a stable, permanent universe like that. And that's why gravitational instability, even very early on, even Newton realized there were issues with gravitational instability that meant the universe couldn't be permanent in that way. It couldn't just stay the way it is all the time. Has to change. Another very important fact is the finite speed of light. Philosophers, scientists had always thought about the speed of light, and tried to wonder whether it might be finite or whether it actually traveled from one place to another with infinite speed. Came up with all different kinds of answers. Galileo, being the premier experimentalist of his time, tried to measure it. He went and stood on one hill, opened his lantern. His friend on the other hill, when he saw the light, would open his lantern, and he would time how long it took to come back. Now that actually works perfectly well for sound, but light travels much too fast for that. And so all Galileo could say is it goes a lot faster than sound. And Robert Hooke, in a lovely phrase, called it exceeding quick. And that's all they really knew about it. Now, there was an astronomer not long after Galileo, Ole Romer, who used the moons of Jupiter as a kind of clock to measure this speed of light. And I'll just give you a rough idea of how he did it. You could go out and watch the moons of Jupiter and see when one of those moons would be eclipsed by the planet Jupiter. And as it went around, that created a kind of clock. You could measure when that happened. And what he noticed is that if you took the predictions of when it should be happening and looked when the Earth was on one side of the sun, and 6 months later when it was on the other side of the sun, there's an extra amount of time involved with the light traveling from here down to here. And that extra amount of time allowed him to measure the speed of light. So it's a wonderful early measurement of the speed of light, which was pretty close to the correct answer. Now, there's a Michigan story behind this that I have to put in. I'm going to give you a couple little Michigan stories today, too. Galileo invented the telescope in 1609. And in January 1610, he turned it to the sky, and it had the most productive month of research of any scientist ever in history. He had an instrument no one ever had before, and he knew how to use it. What he discovered was that the Milky Way was made out of stars. He discovered that Venus showed phases like the moon, proving that it was orbiting around the sun. He found the moons of Jupiter, another little solar system out there. And he saw mountains on the moon. He proved that things up in the sky were not perfect, but were very much like the Earth. An enormously important thing. The reason that I mention this is because the initial output of that research exists on a piece of paper a few hundred yards from here in the University of Michigan Library. This is a letter which is in the special collections of the University of Michigan Library, and it's a piece of paper written in Galileo's hand by him. On the top is the draft of a letter which he sent to the Doge of Venice. Doge of Venice was the head of Venice at the time, and he was a very powerful man. So Galileo sent him a letter saying, I've invented this new thing, and you know, I'm pretty sure you're going to want to have it, because it will enable you to see your enemies before they can see you. So he applied for a military contract as soon as he could. He got it, of course, because the Doge was no fool. And so Galileo was then taken care of for the rest of his life. But that's a draft of the letter. That would be wonderfully interesting in itself. It's just a draft. They sent off the real letter to the Doge. But then paper was expensive, so he used the scratch paper on the bottom. And what's in the scratch paper on the bottom there, historians of science agree, are his original notes of his observations of the moons of Jupiter. All right? So what he discovered was when he looked at Jupiter, there were some stars lined up next to it in a straight line. And for some reason, he looked back the next day, and those stars weren't in the same place. And that wasn't supposed to happen. So he started making notes. He looked at it one day, he looked at it another day, then it was cloudy. Then he looked at it another day and another day, and eventually he figured it out. And you can almost hear him figuring it out on this piece of paper. There it is. One day he sat down and said, oh, they must be going around. And he drew a little arrow. That piece of paper is over here in the library. I've held it in my hands. My students have held it in their hands. It's a pretty marvelous connection to Michigan. Okay, it's also a total aside for this story. All right, but the finite speed of light is essential for this story because it tells us that light takes time to travel to us. The sun, even, is 8.4 light minutes away from us. So when we're looking at the sun out there, if you can see it this morning, you're seeing it 8.4 minutes ago. The nearest stars to us are 4 years ago. The center of our galaxy, it takes 25,000 years for light to get to us from it. And the nearest galaxies take millions of years for light to get to us. So when we look out at things which are far away, we're seeing the past. We're not seeing something like the present. We're seeing what things looked like in the past. The history of the universe is laid out around us in layers, very much like the layers that a geologist might look at. We can see the history of the universe. That's crucial because it lets us study it in a way that we never could if the speed of light was infinite. All right, so we can see the recent past when we look at things that are close to us, the more distant past when we look at farther away things, and if we look very far away, we can see the very distant past. All right, that's a crucial thing. Now, if you remember the Copernican Principle, it's not just us, it's not just we who can do this, because light from us is going out to other observers. All right? Our history is spreading out like ripples in a pond through the universe. All right? Yesterday has reached out past the edges of the solar system. 100,000 years ago has reached the edges of the galaxy. All right? So light from us is going out. It's spreading out. Things that happened long ago, the very distant past, has reached very far out. The more recent past has reached a little farther out. And things that happened recently haven't gotten very far yet. Okay? So this is going both ways, and it's giving you a sense that the universe is not a simultaneous thing. You can't think of the whole universe now. You certainly can't observe the whole universe now. All right? You can only observe layers, and out there they can only observe layers. Now, one last thing I want to say before we really start talking about the Big Bang, and that's to talk about Olber's paradox. Olber's paradox was discussed by a lot of other people besides Olber before it happened, but he gets credit for it. And Olber's paradox has to do with why the night sky is dark. So first of all, the night sky is not completely dark. It's partly dark. This is a very beautiful picture taken at the Cerro Tololo Inter-American Observatory in Chile. And although this is a long exposure, if you stand there, this is what it looks like. You feel like you're falling into the universe when you're in a place like this that's that dark. But it's not completely light. And Olber said, if the universe were infinite and permanent, then it shouldn't be dark at night. So let me explain that. Here's a star. It's a red star. This star, if I bring it closer to you, looks brighter. And if I take it farther away, it looks fainter, right? But there's another thing that happens when this moves closer and farther away. Better just turn it back on. Which is that the size of this thing gets bigger and smaller. So when it goes far away, it gets fainter, but it also gets smaller. All right? And those two things happen in perfectly reciprocal ways, so that the amount of brightness you see per unit area of this star stays the same. It gets fainter, gets smaller. They balance perfectly. What does that mean? It means if the universe were infinite and permanent, then I could look out in any direction, anywhere, and eventually that line of sight would run into a star. And what would that star look like? Well, this tells us that the surface brightness of that star, how much light there is per unit area, stays the same when it goes farther away. So if the universe were infinite and permanent, you could look out along any line of sight and you would run into something that looks exactly like the surface of a star. It would look exactly like the sun. So the whole night sky should be as bright as the surface of the sun. In fact, the whole day sky should be as bright as the surface of the sun. If the universe were infinite and were permanent, had been around forever, then the night sky would not be dark. It would be bright. This was an early clue that something was going on that was more complicated. Now people tended to brush it under the rug and say, well, there must be something absorbing the light. That doesn't really work either, because energy is conserved, and if you absorb light, it's going to come back out again. All right? You can't just hide this. So this was a fundamental problem which was realized long before the Big Bang cosmology began. All right. The origins of Big Bang cosmology come with the discovery of the expansion of the universe. So I want to tell you about why people were working on these things and how it came about that they discovered the expansion of the universe. Edwin Hubble, along with many other people, was trying to understand the nature of galaxies. Galaxies had been observed for a long time. It was known that there were these fuzzy things out there. People argued a lot, though, about whether they were little clouds of gas that were close to us or they were, in fact, island universes, big groupings of stars out there in space. Now, we've seen so many beautiful pictures of galaxies that it's hard for us to believe they had this confusion, right? I mean, if you look at a Hubble Space Telescope picture, there's very little doubt what galaxies are like. But they weren't looking at pictures like that. They were looking at pictures like this. This was a really high-tech picture taken at the Lick Observatory, and it shows the Andromeda Galaxy, and it's a little fuzzy thing. You know, it was much harder to see that this might really be a galaxy which is distant. Now a picture we might take of that would look something like this, and it would be a lot easier to imagine that it might be such an island universe. It's also kind of weird that the universe would have these lumps of stars in it. You know, why wouldn't they just be spread kind of uniformly? Why would they come together into islands? Of course, gravity is the answer for that. So he was working on this problem of the nature of galaxies, and he sought to answer two different questions. First, how far away they are, and what are they made of? Are they made of stars or are they made of gas? And as always in the story, he needed new instruments to do it, and the new instrument that he used was the 100-inch telescope at Mount Wilson, a very beautiful telescope called the Hooker telescope, still there, still used. All right? So his two questions were, how far away are they, and what are they made of? And he was trying to answer those questions. So this question of how to find the distance to something in astronomy is a very fundamental one, and it's one that we always face. One of the most important tools for finding distances in astronomy are things called standard candles, objects whose brightness you can infer from some of their properties. So you know how bright it really is, and then you look and see how bright it seems to be, and you can tell whether it's close or far away. For that to work, though, you have to have a label. You have to know how bright it really is. Something about it has to tell you that. All right? The story of how standard candles like this were discovered is a really interesting one. Its origins are at the Harvard College Observatory at a time when Harvard was even more elitist than it is today. The Harvard College Observatory at that time employed many people. It had a large staff of men whose job it was to build instruments and make operations to run telescopes at night and take lots of pictures. It also had a very large staff of women who were employed at the Harvard College Observatory. These women were called calculators. And their job was to examine all these photographic plates, to measure them very precisely, and to keep incredibly detailed records of those things. There were a number of remarkable scientists among this group of Harvard calculators who had an enormous impact on astronomy. The one that's most important for our story today is Henrietta Leavitt. What Henrietta Leavitt discovered was that in her survey of stars, she found a certain kind of variable star that had the kind of label that's needed in order to measure distance. When she did that, she was ready to tell people about it, to publish it. So she did. She wrote it up. She handed it off to one of the few real astronomers who were there at Harvard, and Edward Pickering published it. The author is Edward Pickering. Now, to his credit, it says right at the top, this note was written by Miss Henrietta Leavitt. But she wasn't allowed to be the author. She was only allowed to do the work and make the discovery and stuff like that. Anyway, it's a famous story. There's a picture of her. There she is, working away. All right. This was really the heroic era of astronomy. You know, doing these things back then, I can't imagine. The tools we have now make it so much easier to do these things. They had to examine thousands of photographic plates, and they would do things like blink the photographic plates, going back and forth between two plates. And if you look closely at this picture, you'll see something. There's a star in the middle that's changing. All right? So they had to look at thousands of these. She was able to pick out about 1% of the stars as variable stars. And then she had to measure many, 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 many observations of them in order to understand what they were, keeping them all in very neat columns and notebooks. Right? A very heroic kind of endeavor. The particular object she was studying was the Small Magellanic Cloud. The Small Magellanic Cloud is a dwarf galaxy which is not far away from us. And it has the wonderful feature that because it's a discrete object at a fixed distance, when we look at stars in the Small Magellanic Cloud, the brightness they seem to have is directly correlated with the brightness that they are, because they're all at the same distance. So if I see two stars there, one of them looks bright and one of them looks faint, the bright one really is bright and the faint one really is faint, at least compared to one another, because they're all out there at the same distance. Just like when you look down out of the airplane at the city of Chicago, all those lights you see, their brightness is real, right? Because they're all out at the same distance. What she found is that if she looked at a certain kind of variable star, a very small fraction of the 2,000 that she discovered, they were called Cepheid variables. They were very bright, and they had this neat property, that ones which pulsated slowly were brighter, and ones which pulsated fast were faint. The pulsations, the way they pulsed, was a label. Just said like 100 watts on the light bulb. You could read it, and it could tell you how bright the star really was. So by reading this label, you could figure out how bright something was, and then if you saw whether it looked bright or faint, you could tell whether it was near or far away. Right? It's a way of measuring distance. All right. This Cepheid period luminosity relation is a label describing how bright stars really are, and this was the big contribution that Henrietta Leavitt made to it. What did Hubble do with this contribution? Well, he had the 100-inch, most powerful telescope in the world. He turned it to the nearby nebulae, like M33 here, the Triangulum galaxy, and he was able to show that there are individual stars in this picture. That was the first contribution. Galaxies were made of stars. Some of those stars were Cepheid variables, and he measured their light curves, their pulsations. He saw that they pulsated. They look just like Henrietta Leavitt's variables, except they're way fainter. And that's because M33 is way farther away than the Small Magellanic Cloud. So in one swoop, he proved that there were stars in them and that they were very distant. All right? So he set out to understand the distance to galaxies, and he did that. At the same time, other people were trying other ways to figure out what galaxies were made of, and one of them did another kind of heroic set of observations, a man named Vesto Slipher, which is certainly one of the great names in the history of astronomy. What he was doing was taking spectra of galaxies. And to take a spectrum, you take the light from a galaxy and you spread it out so that you can see all of its different components. And we have a tool over here to show you a little bit about the spectrum of an object. We have a lamp inside here, and we'll turn on that lamp. And then we're going to do something which will allow us to visualize the light that comes out here and see what different colors it has in it. All right? Okay, so a little flame there. What we're looking at is the light from inside here. And you can see right now that this camera is seeing light which is red. And if I move the camera over to the other side, you'll see light which is green, and you can see how much blue light there is in it. So it has blue and green and red light in it. It looks white coming out of the box, but it's blue and green and red all mixed together there. All right? Now, Slipher could use the spectrum to measure more than just sort of what colors were in there, because he could detect particularly what kinds of elements were inside the galaxies. And I want to just show you that by dipping this little paddle in some salt water, and then I have to heat up that salt. And when I heat up the salt, it will go into a gaseous form, and it will absorb some of the light. So when I put this in here, we'll get some gaseous salt in there, and right there, you see those two dark lines? When I remove this, they disappear. All right? What we're looking at is absorption from sodium, from the salt gas that's being heated up and put into there. Those lines will appear if there's hot sodium around, and they won't if there's not. So when he took the spectrum of objects, he was able to learn things about what they were made of. Those particular lines show up at very particular places, and consequently, he could tell what elements he was looking at when he looked at them. Slipher discovered another thing as well, which had to do with the fact that objects which move relative to you and emit waves of different frequencies. This is a pretty well-known effect. Doesn't take a lot of demonstration, because you've all seen ambulances with sirens come racing down the street. And when they're coming towards you, the frequency is really high, and when they pass and go away from you, the frequency is low. That can be illustrated with this little demonstration. Loud and annoying. So you hear the changing frequency. That's because when it comes toward you, it's higher, and when it goes away, it's lower. And it's very annoying. All right? The same thing happens with light. If an object is traveling toward you, its light will be shifted toward the blue, toward higher frequency and shorter wavelength. And if it's moving away, it will be shifted toward the red. So Slipher used this fact that the light would be shifted a little one way or another. He looked at those lines, he watched them shift a little bit, and measured the velocities of galaxies, and found a big surprise. He found that all the galaxies he observed were moving away from us. Pretty fast, too. Like the lowest speeds were 300 kilometers per second. That'd get you from here to Michigan City, Indiana in a second. Pretty fast. How could that be? How could everything be moving away from us? What happened to the Copernican Principle, that we're not in any special place? All of a sudden, everything's moving away from us? Could we be at the center of everything? As far as Slipher could tell, and as far as we could tell without more information, it did look like we were at the center of everything. All right? So what was the more information that put this together? Edwin Hubble took Slipher's observations of velocities and his observations of distance and just plotted them. Here's the distance. Here's the velocity. And what he found was a surprise. Things that are farther away are moving away from us faster. This is the velocity-distance relation, which is inscribed in a very simple equation that says the speed that things go away is a constant, Hubble's constant, times the distance. More distant things are moving away from us faster than nearby things. This connection is essential, because without it, there would be no way to explain Slipher's observation that everything's moving away from us. All right? But with it, there's an easy way to explain it. This velocity-distance relation provides a clean explanation for why everything's moving away, and says that every observer, not just us, everyone in the universe will see everything moving away from them. The way it works is like this. If you have a universe which is a certain size, and 4 galaxies are a certain distance apart, and you take that universe and you just make it bigger. You stretch it out. Every galaxy moves apart from every other galaxy. If I sit on any one of these galaxies, I see all the others moving away from me. All right? If I let it go a little farther, I still see them moving away from me. Furthermore, the velocity-distance relation is there. If a galaxy is close to me and the universe expands, there's not much universe in between to do the expanding, so it doesn't move away from me very fast. If it's a very far away galaxy and the universe expands in between, then it moves away from me fast. The velocity-distance relation is the essential piece of this. If everything was moving away from us, but we didn't have a velocity-distance relation, there'd be no explanation. So it's essential that this should be there, and that's the thing that connects us to say the universe is really expanding. That's really what's going on. Without the velocity-distance relation, it wouldn't be there. Now, you might think Hubble's diagram was not all that convincing. Yeah, they maybe were going a little faster away from us. This has, of course, been carried through, and in the way of all important discoveries in science, we have now gone hundreds and thousands of times farther than Hubble did, and the relation works. Right? That's what happens when you find things that are true in science. You test them really hard, and they continue to hold up. That's the important thing. So Hubble's original measurements were down here, all right? And we now measure things all the way out like this, okay? He had no idea whether this would be true. Could have been wrong, but it wasn't, right? It's a real test. Another way of saying this is to say that there are no objects out here very far from us, none, not one, that isn't moving away from us that fast. The only way to explain that is with expansion. And with expansion, it's an easy explanation. Now, what does it really mean? We usually talk about this as a velocity-distance relation and say that the velocity of that object out there is very high, right? But that's not really true. What this is really measuring is something different. And you can see that because when light leaves a galaxy out there, it takes maybe millions of years to reach us, even billions of years to reach us. So we don't have any idea what that galaxy is doing now, right? We're not measuring its velocity. What we're doing is we're measuring what has happened to that light since it left. It leaves with a certain wavelength, it travels through the universe, and the universe gets bigger underneath it, and it stretches out. What we're measuring is how much the universe has expanded since that light left. All right? It's not a velocity. It's a measure of how much the universe has expanded and how much the light has been stretched. There isn't any kind of simultaneity in the universe. There's no way that we can tell anything about what's happened to that galaxy right now. We can only see what it looked like millions of years ago. We can't know what's happening at this instant across the universe. We can only see these shells wrapped around us. So redshift is not measuring velocity. It's measuring how much the universe has expanded since the light left. And so I want you to think about the Hubble distance velocity diagram in a different way. What the distance shows us is how long the light has been traveling, because light travels at a finite speed. So if you know the distance, you know how long the light has been traveling. And what the redshift shows is how much the light has expanded since that time. So it's a measure of time and expansion, right? It's not just a measure of velocity and distance. So if we put that same diagram up here again, this time, there's a distance, right? So I can turn that distance into the amount of time it took light to travel. This point out here is 1.6 billion years. And this point up here corresponds to 10% stretching of the universe. So in the last 1.6 billion years, the universe has expanded by 10%. That's what this Hubble diagram is really telling us. Now, people have carried this much farther. I'll just show you a diagram to give you a feeling. Here, at about 9 billion year light travel time, are objects observed at a time when the universe has changed by 100% in size. It was half the size of what it is today then, and it's grown by a full 100%. Okay? This cosmic expansion is as real as anything gets in science. It's real. It's a fact about the universe. And any story for the origin of the universe, any cosmology you want to have, has to explain this. You can't ignore it. It's a fact about the universe. All right. Expansion has implications. In particular, it says something about the past. Now the universe is expanding. In the past, everything must have been closer together. Doesn't mean the universe was smaller. The universe could be infinite right now, and it may have been infinite at every time. But everything that we see now was closer together. All right? And since it was closer together, it must have been denser. And when we squeeze things closer together, they get hotter. And I have a little demonstration to show you that. Measured behind me here is the temperature inside this little tube. If I squeeze it, the temperature inside the tube, I pulled it over, goes up. And if I pull it out, the temperature inside the tube goes down. All right? Squeeze it, the temperature goes up. Pull it out, it goes down. So that's expansion. There's a slightly more dramatic form of expansion. After all, you might think the temperature is dropping only because I'm pulling on it. That's not actually true. Here's a canister of CO2 gas used to put out fires. It's very high pressure inside, so when I squeeze the handle, it's going to expand. And when I do that, it's going to cool off. All right? So it does make a loud noise, I'll warn you. Okay? It expands, and what is it producing on the floor there? Looks like dust, but it's not. It's actually dry ice. Cold, frozen carbon dioxide. Not cold because this thing is cold. Cold because when it expanded, it cooled. So when things expand, they really do cool. It's not just that, I make them cool by pulling on them or something. So this idea that the universe was denser and hotter is inescapable. And at some point in the past, the universe must have been very dense and very hot. All right? So what does something look like when it's dense and hot? Well, we know what heat does to things. It causes changes in state. Things go from solids to liquids to gases to plasmas where you tear apart the atoms, and eventually to quark gluon plasmas where you tear apart the protons and neutrons. Things fall apart when you make them hot. So in the beginning, when it was very, very hot, it really was just a mix, a uniform mix of stuff. What did it look like? Well, hot things emit electromagnetic radiation. This is a hot burner on your stove. And we need to know something about what that radiation looks like. Could we see this radiation from the early universe? If you remember this idea of cosmic archaeology, it's true, you could. You could look out, and you would see things that happened recently nearby, and things that happened earlier farther away, and things that happened earlier still farther away. And eventually, when you looked out, you would be looking far enough to see some stuff which emitted light when it was really hot in the early universe. And that stuff, that light, has been coming toward us all that time, and just today, it got here. Where would you find it? You could look anywhere. Because in every direction, there is a distance far enough that you will reach that point where light was emitted from that spot when it was hot right in the early universe. It's been coming toward us all that time and just got here. And if I look over there, there's a place the same way. And if I look up and down, anywhere, I should see it. Because it's just shells of time that we're looking out at. What about us? Was it hot and dense here? Sure it was. So where's the light from that? It left. It's out there at the far edges of the universe. It's out here on the outer ring. Our light is just getting to them, just as their light is just getting to us, if there's any them there. All right? What would it look like? Well, we need to know what the light from hot things looks like. And so you need to think about how you see something. What is the light you see coming from something? Most of the time, the light you see coming from something is reflected light. This table right now is not emitting light that you can see, but you can see it anyway. That's because it's reflecting light from the lights that are in the room. Most of the time, that's the way you see things. And when you do that, things look very different one from the other. The light that is reflected from things looks very different. And so we'd have to think hard about what the early universe would look like if it was reflecting light. But it's not reflected light that we see. It's emitted light. Objects, in addition to reflecting light, can also emit light. And it turns out that if something doesn't reflect any light, but only emits it, it has a very simple kind of light that it emits. This was first noticed by an interesting character named Thomas Wedgwood, one of a very famous family of British makers of porcelain, also early scientists. This guy was the uncle of Charles Darwin. He lived an unhappy life. He ended up experimenting a little too much with opium in his life. But he did make some discovery. And his discovery was that when he put things in his oven, everything he put in his oven looked the same. It didn't matter what it was made out of or what its shape was. They all looked the same. So I want to show you that. At room temperature, everything in the oven here looks different. That's because it's reflecting light. And I said that things would look different when they were seen in reflected light. If you take that same oven and you heat it up to 800 degrees centigrade, you can start to see what Wedgwood saw. Everything in there is starting to look very similar because you're not seeing reflected light anymore. What you're seeing now is the light that is emitted from the object. It's not bouncing off and coming back to you. It's just coming out. And this light which is emitted by any object which only emits light and absorbs any light that hits it, it doesn't reflect any light, any object which does that will look exactly the same. This is something we now understand exquisitely well. It required the invention of quantum mechanics to understand this thermal radiation that comes from objects. It wasn't something that these guys knew about, but it is true that we have a very solid explanation for where this comes from. It says that all objects which only emit light emit the same kind of light, the same spectrum of light. It says that hotter things are brighter. That's not an unfamiliar thing. It also says that hotter things are bluer. And that is a little bit of a surprise to a lot of people. When you look at a candle flame, for example, the blue part is the hot part, not the red part. That might be a little surprising. If you look at things at different temperature, they all emit thermal radiation, including everything in this room. But the thermal radiation that's emitted by the sun at a high temperature, like 6,000 degrees, comes out in the visible region where we can see it. The thermal radiation from something like those things that were in that oven looks very red, because most of it actually we can't see. But a little bit of it leaks into the visible, and more of it on the red side leaks in than on the blue side, so it looks red. If you keep heating that thing up, eventually it'll look blue, like the flame I showed you over there. All right? Now, the stuff in this room you don't see, because essentially none of it is in this visible region. It's at longer wavelengths. All right? So the color changes and the brightness changes. So what would the hot early universe look like? It's thermal radiation. So it should look like any other hot thing. Well, how hot is it? What we're going to see is the universe when it's so hot that we can't see through it anymore. Because if we could see through it, we would still see farther things, right? So you keep going until a point where you can't see any farther, and what you see then is material that's so hot light won't go through it. It's a plasma. It looks like the surface of the sun. A hot plasma that you can't see through. All right? So what we should see when we look out at the sky is, again, something like Olber predicted. We should see the sun out there on the surface of the sky. But that's not all there is to it. What we will see now is not that, because that light which left then looked like the sun has been stretching ever since that time. All right? So instead of seeing the visible light that we can see with our eyes, what we see is no visible light. You see radio waves, because the light has been stretched out that much. That's why you don't go out at night and see the Big Bang. It's out there, it's really bright, but it's radio waves. You don't see it. All right? This was thought about and predicted by people in the 1940s and then really revived at Princeton in the early 1960s. And I want to mention this guy who's really the godfather of understanding all these things, because he also has a Michigan connection. This is David T. Wilkinson. He was a professor at Princeton University, but he got his degrees, a bachelor's in engineering, a master's in engineering, and a PhD from the University of Michigan. So a great product of this university. He just died a few years ago, and the Wilkinson microwave anisotropy probe is named for him. Really remarkable guy. So this cosmic noise, this radio light that should be coming from everywhere, where is it? Well, these two guys, Penzias and Wilson, two of the luckier guys in the history of science, were assigned to use this radio telescope that Bell Labs had originally made to bounce communication signals off of balloons with. They wanted to use it to do radio astronomy, but they had this noise in their antenna. It seemed to come from every place, and they went inside the antenna and they cleaned out this dielectric substance which was in there, which was pigeon poop. And that didn't fix it, so they kept trying to figure out what it might be, and they just couldn't figure it out. So they went up the street to Princeton and asked these guys at Princeton, do you have any idea what this might be? And it turns out that this guy, Dave Wilkinson, had the radiometer on his lab bench. Right? They were ready to take it up to the roof and measure this, because they knew what they were looking for. But what happened is that the Princeton guys published one paper in the Astrophysical Journal. The very next paper was Penzias and Wilson's discovery. Penzias and Wilson won the Nobel Prize, and the Princeton guys didn't. And I knew Wilkinson pretty well personally. He was wonderful about this. You know, he knew that. He just thought it was a wonderful part of the way science works. You know. And what was most important to him was that it was true. Not that he won the Nobel Prize, right? Okay. So this has since been expanded, and the most important step in recent years was the launch of the Cosmic Microwave Background Explorer, a mission that Dave Wilkinson led. This went out into space to measure the microwave background radiation because it's much easier to do it precisely there. And it was launched in 1989. It made an image of the whole sky. Remember, the idea is you should see it everywhere. They wanted to look and make sure that was true. And it made very precise measurements of this and reported those results not much more than 15 years ago. What did COBE find? When it looked out at the night sky and it took a picture of the radio waves that were coming from the sky, it saw a perfect black body spectrum, exactly the radiation that was predicted. What's shown in this figure is the spectrum that they measured. Sorry, the data points are a blown up version of the spectrum that they measured, and underlying theory underneath it. Now, for those of you who understand how these error bar things work, what's been done here is to magnify the error bars by 400 times.
Oh my gosh.
So they're really, 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 really much smaller than the line. Okay? This is the best black body we've ever measured. Better than what we can measure in the lab. It really is that kind of black body radiation. Here's another representation of that. This is the difference between the theory and the observation measured in units of temperature. Okay? And what you can see is this is 2.724 degrees. This is 2.726 degrees, 0.002 different. Right? It really agrees. All right? That's an exciting, very fundamental thing, the fact that these agree. It's the most perfect such spectrum we've ever seen. What did it look like when they looked out on the sky? It's supposed to be everywhere. That's what they found. It was everywhere. So if you take the sky and you unwrap it into a kind of an oval shape like this, so this is showing you, let's say, the North Pole and the South Pole and everything unwrapped. So it's the whole sky. This is what it looked like. If you show it on a temperature scale which goes from 0 to about 5 Kelvin, this is what it looks like. Completely uniform. All right? Now it isn't, it turns out, completely uniform. And if you turn up the contrast, if you look very closely at the temperature in this plate and you amplify the fluctuations, what you see first is some features. You see something very interesting looking. There's a place where the sky is colder and a place where the sky is hotter. Okay? Now that's a real signal. It's interesting. It's called the dipole of the microwave background, and it comes about from the Doppler effect. We're moving relative to the microwave background in some direction. So in the direction that we're moving toward it, it looks bluer. In the direction we're moving away, it looks redder. You can see the pattern has all the symmetry you would expect. There's one place that's hotter, one place that's colder, and in between, it goes in between. Okay? So this can be removed. This signal can be removed. We can model it very simply. You see now that the amplitude of these fluctuations is 3 millikelvin, 0.003 Kelvin. It's 1,000 times smaller than the actual temperature. And if you remove that dipole and look again, what you see looks like this. Now the fluctuations are 18 microkelvin, 18 millionths of a degree. And you see two things. There's a big thing across the middle, and that's the Milky Way. And it turns out that there's other cold stuff out there, not just the microwave background. There's dust, which is cold too, mostly in our galaxy, and it emits this microwave radiation. We see that it's mostly in our galaxy. But looking away from the galaxy, there are fluctuations which we now know are real. And we'll talk more about those in the next lecture. So, just like the expansion, the cosmic background radiation is real. It's a fact about the universe. Any story for the origin of the universe, any cosmology, has to explain the microwave background radiation. Can't make it go away. So what happened even earlier? Let's just go through this real quickly. Earlier, the universe was even hotter and denser, and it looked like the inside of the sun. At some point in the past, it was hot enough for nucleons to build, to form elements. And so nuclear burning, putting together hydrogen and helium into iron and heavier elements that are heavier up to iron, releases energy. So it will happen naturally if you make the conditions right. Just like this paper will release energy if I make the conditions right. If I put this in a place that's hot enough by putting a lighter under it, it'll burn naturally. If you put nuclei in a place that is hot and dense enough, they'll burn naturally. It will happen. So all you have to have is really hot and dense conditions, like in the early universe. These three gentlemen, honest to God, named Alpha, Beta, and Gamma. It's said that they looked around for a man named Delta, but couldn't find one. Okay? Alpha, Beta, and Gamma published this modest little paper. It was in the letters to the Physical Review, Communications not more than 600 words in length. And here's their title, The Origin of the Chemical Elements. Pretty brave thing. And what they did is they published this little paper that said, oh, we know why there's 76% hydrogen and 24% helium in the universe. It's because in the early universe, when those elements were being burned, when they were being formed because it was hot and dense, it didn't continue to burn all the way up to iron because it didn't last long enough. The universe was expanding and cooling. There was only enough time to get you to helium. Not enough time to get you all the way to the heavier elements. And so if you want to make the heavier elements, you've got to start over, form a star, and make those hot, dense conditions again, because the early universe didn't last long enough to make that happen. They could predict just how much stuff there ought to be as a function of the density of material in the universe, and these are sort of modern versions of that. And the current state of these measurements is good general agreement. The most important agreement is that it explains why the universe is mostly hydrogen and helium. You have to have an explanation for that, and this is a natural explanation for it. The burning in the beginning was brief. If it was long, it would have burned all the way up to iron, and it didn't. Okay? There are, I will say, some detailed disagreements right now between observations. These boxes show you the measured density of these things and the prediction, which is this line. All right? It's difficult to measure how much hydrogen, helium, lithium, and so on was in the early universe because it's been altered since then. So you have to work really hard to be careful to make this measurement. So although these don't agree perfectly right now, they agree well and especially explain the predominance of the light elements in the universe today. So this is something that's still being very much worked on. This dominance of the light elements in the universe is real. Hydrogen and helium are the most important elements in the universe. Another fact about the universe that an origin theory, a cosmology has to explain. So there are 3 pillars of the Big Bang. There are more than 3 pillars on Angel Hall. All right? So we'll magnify it until we have only 3 pillars. The 3 pillars of the hot Big Bang are the ones that we've talked about today. Cosmic expansion. Dead clear thing. You can't miss it. It has to be true. The microwave background radiation. We see it everywhere we look in the sky. It looks exactly like it was predicted to be. And the light element abundances. These 3 things are called the 3 pillars of the Big Bang, and they were around in 1990. We knew that these things were pretty much true. And so there was a lot of confidence that it would turn out to be right, but not enough to really settle it. And this hot Big Bang picture, built on these three pillars, has evolved over the last 10 years into a theory which has been tested in yet another series of ways that we'll talk about in the next lecture, so that you can hopefully get a sense of why it is I'm so confident when I say this. We'll talk about this basic Big Bang picture and say that cosmology, has to explain these things. Any cosmology has to explain these essential facts about the universe. There are questions which remain, though. The universe was completely uniform. How did it get to be not uniform? We have to have an explanation for that, too. So we're going to talk about that next time. There's a little mystery that we glossed over in our discussion. How could the universe be so uniform? And there's a physical problem with that has to be settled, still kind of in progress. And also this question of what is it that makes up the universe. This model, which we had in 1990, made predictions for these things. And over the last decade, we've been testing them and finding out more and more about how the universe has evolved from that early time. The picture has only strengthened. And consequently, everyone in the astrophysics community really thinks this has arrived at the level of confidence that we assign to things like the Ice Age. These things really happened. And it could be that our picture of the Big Bang, somehow the theory could be wrong, but the observational facts are just there. We can't get away from them. And so we're going to have a good way of explaining them. So far, the Big Bang picture of the universe is the best picture we have for understanding them in a simple framework, and so that's why so many people have come to accept it.
Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.